Hello everyone. Today we're looking at a solution of an exam practice question from the Pearson Edexcel A-Level Physics by Mike Benn, Graham George, and Tim McCrail by oafthe Education. This is Module 1, recommended question, and I have chosen this problem because I feel like this might be mathematically and physically the most puzzling thing that is offered for this concrete unit. So first of all, we need to analyze the problem properly. So an oarsman rows a boat across a river, aiming for a point on the other bank directly opposite. Directly opposite is one of the main points. His starting point 40 meters away. Okay, so what we start with, we're going to make a drawing, and I want to do it nice and neat, so it is going to be exactly with the ruler. Okay, so I'll make little lines which will state that the surface is not moving. Physicists often do that. Okay, so let's continue. So as you understand, here we are given 40 meters away. So we have to state the scale. So one cell will be 10 meters. Okay, so let's get back to the ruler. Choose, I don't know, like some other color. Any random one would be nice. And go with it. Okay, so let's get back to the main colors. Oh, it's fine. So this is the point A where the oarsman started moving. This is the point B where he wanted to get. Now, so this one is 40 meters. Let's continue reading. So he rows at a velocity of 2 meters per second. Well, we'll state what that means for us a little bit later. So towards this point, but he finds that he reaches the other bank 10 meters downstream from the intended target. Okay, so we need to state where the stream is going. For that, I will choose another color, for example, this one. Okay, so this will be the vector that will symbolize the direction of the stream. Okay, V stream. This is the direction of the stream. Okay, so next, and 10 meters down the stream. Okay, so that's one of the main points, and that's actually legit for us. Okay, so the other bank 10 meters downstream. Okay, so this is the point where he ends up. Okay, so we should state that A, starting point, B, point where he wanted to get, C, the final point where he actually got. Okay, so I want to move the scale to another place. Let's say, let's leave it here, right at the beginning. Right, let's continue. So that means that we have a little thingy here that is 10 meters. Okay, let's put it in here, 10 meters. All right, that's very nice and neat. Okay, here should be good. All right, whatever. So 10 meters. All right, so what have we found? We have two vectors, and well, they're not actually vectors. Let's say these are just some distances, some length, whatever, because the actual vector in here, it will be the vector of displacement, and this one will make completely red. So he started in A and he wanted to go to B, but instead he moved down this downstream again for 10 meters and he ended up in C. What does it mean for us? It means that the distance he covered is not 40 meters and it is not 10 meters either. It's something in between of their sum. Okay, so basically displacement by its definition is the shortest vector from the starting point to the final point. So let's draw this. So this is the vector of displacement, okay? And we can actually state it even. We can just write it displacement. Okay, so that's not the end for us. This is far from the end actually. We need to continue with it because right now we will need to turn to the velocity that we are given. So we have some extra space in here. So I need to delete the extra part. Okay, so this is the extra part that is given to us. All right, so what we need next is we need the similar thing, because we will make a similar diagram but with velocities. So what you have to remember is that these kinds of diagrams, according to the unit information and generally this part of the book, they can be made with displacement, with velocities, with forces, sometimes no, actually displacement and velocity mainly. Okay, yeah, so we also need to make a similar one with velocity. All right, so we'll draw up the exactly same bank, exactly the same. Where did it disappear? All right, got it. Let's draw it up again. It's a minor lag. All right, and this one. And now we'll talk what it means for us. So here the scale will be different actually. So still we'll need to say that this is a surface that's not moving, that it's a bank of the river that is not moving. Okay, so still we drop the starting point in there. I'll choose some green for that to show that this is a different vector. So this is the point where he got. So this is the point where he actually got. So the comment to this thing is exactly the same. But now we need to draw. And what we will draw. So we are given the information that he rolls at a velocity of 2 meters towards this point, which means the point B, okay? A velocity towards this point, and in the comment B. Okay, so his vector of his own velocity is directed right in here to B, okay? And this one is equal to 2 meters per second. Okay, so we also know that he ended up in the point C, not in the point B, which means that velocity also has another component. And now we get back to the speed of the stream actually. Okay, we can put it right in here. All right, so what it means for us, that there is a vertical component, and we'll drop it right in here. Okay, so this kind of velocity is actually the velocity of the stream. Velocity of the stream. And 2 meters per second is the velocity of oarsman, VO. So let's state that. So VO, velocity of the oarsman, and Vs is the velocity of the stream. So now, which you probably understand, that right as the displacement, the resultant velocity vector was also pointed from A to C. So we need to draw the resultant vector. Now, let's get back to reading the problem. So from the intended target, sketch a vector diagram for his journey. We have done that. And calculate the velocity of the boat between the start and finishing points. So since the starting point is A, the finishing point is C, we need to find the resultant velocity, which is, let it be just V, okay? Just V. V will be the velocity of the boat between the start and finishing points. Okay, so in the problem actually we have a hint that 2 meters per second is not that velocity that we are trying to find, because at first it jumps right into you, because they say that he rose at a velocity of 2 meters per second. They don't say that this is the velocity of the boat. Let it be even like that, okay? And we need the velocity of the boat, okay? So these are two different velocities, actually. These are two different things. So that's what we are trying to find. Now that we have the diagrams and we know what we need to find, we need to understand what we have and what we can do with it. So we have this and we have this. But also, most importantly, we have a certain angle. This angle. And we'll call it a theta angle. Okay, so we know this angle, so let's continue with that. So what I understood is that we can use the trigonometrical function tangent to solve this problem, but in order to do that correctly, we need to combine the data from the first diagram with displacement and the second diagram with velocity. So let's begin. We're given the angle theta, and I say that tangent of theta is equal to, and by definition tangent is the opposite side of the triangle to the adjacent. Okay, now let's find the opposite and the adjacent in the diagrams that we actually have sketched. So if we take a look at the diagram 1 with displacement, the opposite to the angle theta is this side, right in here. So this is 10 meters. The next thing, we take the adjacent, and the adjacent is this side, it's 40 meters. And now we basically have found the tangent for this angle, which is 0.25, as you have understood. 0.25. But what you haven't understood yet is that we can actually use this tangent for the second diagram, because the opposite side of the second triangle that we have is this. And this is, guys, this is the velocity of the stream. And the adjacent is the velocity with which the oarsman is rowing. So this is going to be VO. Okie dokie. So this is how we got here, and this is the main conception of this problem, how you get from tangent to this statement. Okay, so basically what you get from here is that you can find the thing that is missing, because from the problem we know what the velocity of the oarsman is. Now we know the ratio, and we need to find this part, which is actually missing. Okay, so let's make the velocity of the stream a subject of this formula. Okay, which means that velocity of the stream will be 0.25 of the velocity of oarsman. And boom, we are moving forward really damn fast. Okay, we don't need a ruler anymore. Okay, which means that the velocity of the stream is 0.5 meters per second. This is the velocity of the stream. Okay, so now you understand. Let's take a look at the picture again, the diagram. So now we know the velocity of the stream, and we also know the velocity of the oarsman. We can find the last component. For that we need the Pythagorean theorem, and that's very easy. Okay, so this was the first step. This will be the second. So the final velocity is the square root of the sum of the square of the stream's velocity and the velocity of the oarsman. Okay, now let's put in the numbers, and whatever, you can just simplify that to the square root of 4.25 meters square second square, like that, power -2. Okay, so approximately this is 2.06 meters per second, which is actually equaling the number that is given to in the book answers, which is approximately 2.1 meters per second. So this is our final answer. What you shouldn't forget about is that in A-level papers you need to write down the answer. Now, some of the students that have tried to solve this problem and that have inspired me to make this video, these are the students who were working using the conception that from the diagram 1 with displacement vector, they can actually try to find the time. Okay, so what they were saying was that the time that the oarsman took to travel from one bank to another was 40 divided by his speed, which was 2 meters per second. Guys, this is completely wrong, because the trajectory at which the oarsman was moving was not 40 meters long. Okay, because to find the time we need to divide the distance by the time. Okay, and distance, guys, is the distance length of the trajectory. Guys, if you take a look at this picture, at this diagram, 40 meters is not the distance that he traveled. He obviously traveled from A to C, not from A to B, and AC can't be 40 meters long. It's approximately that. So the guys they have just found some similar numbers, and they were actually able to get to similar answer, but it's the wrong way of solving this problem. Why? Because let's choose another color. The trajectory at which the oarsman was moving was approximately this curve. And as you can understand, by no means this distance can be equal to 40 meters or to the displacement, because this is having completely different length. Well, maybe not like completely, but it's a different number. So from the physical standpoint, it's wrong to use this conception. So this conception, guys, is wrong. I only see the solution through the tangent as the correct option. So good luck with your studies, good luck with your A-level, and I will try to supply you with more solutions throughout the course.